Good afternoon, everybody. Yes, good afternoon, everybody's attention. Yes, yep, my name is Jeremy Hong, and glad to be presenting here in Dayton, Ohio. I've always wanted to present this specific topic here. Last year, I did a series of presentations on hardware reverse engineering, but that actually never really came here to home, and I'm really glad to present in front of friends and others from the local area. And so here we go. So yep, my name is Jeremy Hong. I'm from here. I'm a systems engineer for a local aerospace and defense contractor. Started a company back in 2012 called Hong's Electronics, which even to this day still do a little bit of consulting, as well as contributing back to open source hardware. Very big supporter of the Open Source Hardware Association. So check out their conference coming up here next year in March in New York City. And I'm a big amateur radio operator. My call sign is KDATO, and also that's a really nice point of, as the previous presenter pointed out, from open source intelligence. Wow, you can figure out everything from my call sign pretty much, as far as personal details. But yeah, as I mentioned, previous presentations are from based on the topic of hardware reverse engineering, are from Teardown, TourCamp, and PCB West. The one that I'm presenting today will be based off of my PCB West presentation because that one was not recorded. And so, that one gives an interesting perspective on this topic because a lot of people, like the names of like Joe Grant, Sammy Kamkar, and others, have presented a lot of detailed hardware RE expertise and techniques from the attacker perspective. But I'm now going to present to you from the defensive perspective, you know, the blue team perspective of product security and such. And so here we go. Yep, we're going to do a little bit of brief introduction. What is PCB RE to begin with? The current sad state of IoT devices. Knowing what your adversary, at least my perspective of knowing all you hackers. And then some examples of attacks, you know, going back to the point that obfuscation is not security, effective circuit design countermeasures, effective PCB RE countermeasures, which are kind of the same thing, and sort of like a resources slide, and then conclusion, and then there's some more resources slides that you can go into in your free time as well. So, yep, so there, actually, even on the non-security side, there are a lot of reasons for PCB RE. You might have an old system that needs to be updated, or if you're trying to fix something that is not necessarily, you don't want to really replace or at least update, you just want to keep the design just because it works, you kind of have to know how the older design works. So there's a reason for reverse engineering that, and that's where like a lot of legacy hardware is a huge reason for PCB RE. And the same thing with recovering a lost design, because over time, as you know, documentation schematics will kind of just fade into the ether, you know, links go down or either old literature is lost. And so that's the reason why you want to reverse engineer stuff. And then there are the legal side of things where you want to have a competitive edge over your competitors. So you have corporations trying to figure out what their competitors doing as far as like, oh, how do they implement this in hardware and such, as well as like, oh wait, that's our tech. How do they steal it, or how did they implement a very similar feature? So there's patent IP enforcement. As far as I know, there are actually like firms that's kind of like their tagline is, where they're reverse engineering firms for hardware that are there just for providing support and evidence for patent IP kind of cases. So that exists. And the focus of this presentation, of course, is focusing on those red team hackers in hardware, or on the or other red team hackers, and hopefully we'll provide you with a little bit of different insight and perspective as far as on the design side, which is where I am at. And yep, mentioned most of those. Yes, so current state of IoT devices, even in 2019, it's still virtually non-existent. As we know, it's very easy to find a lot of IoT devices where they still use default creds, and once you get one, that's the entire network that goes down. So, and of course, whenever you open these things up, as I'll show later, a lot of boards, they still in silkscreen put, hey, here's the JTAG, here's the UART, here's the single wire debug interface, just like I'm open. And it's very rare to find manufacturers and vendors that actually turn these features off, even though the systems on chips and microcontrollers that they use actually have those features where you can turn off and provision access to those kinds of ports. And yep, there's not going to go into them all, but yeah, there's of course numerous attacks and proof of concepts over time, for physical and remote. And yep, just continuing. Yeah, you see this getting into as well as fax machines, as noted from one of last year's talks at DEF CON, What the Fax. Very interesting attack on attacking fax machines using like a legacy color format to actually compromise the fax machine and then get onto a network. Very scary, very cool at the same time. And you see this also happening with critical infrastructure and PLCs, because those are all network devices. Some of them still are public facing even. And I see Mike laughing back there. Yeah. Yep, so in this talk, we're going to assume that any IoT device, any consumer and commercial computing systems that do not require human-to-human or human-to-computer interaction, and most importantly, are connected via the internet through a public-facing network device. And also, we're assuming that in this talk that we're mostly focused on like level 1 and level 2 hackers, which are kind of like your script kiddies or just like your hobbyists like us, who don't really have access to nation-state level tools, but we'll still go into those a little bit later, because there's a lot of cool stuff coming onto the scene that even if you wanted to, could actually contact a local university, and then you could actually rent out some equipment to image different kinds of chips and all sorts of stuff. Yeah, very scary world right now for us hardware designers. So yep, I mentioned, yeah, these are our assumptions. And yeah, I've developed, because over time working even for a company that did cybersecurity, I appreciate a lot of these points now more than ever, because it takes a lot to run a hack, really. And as even in the previous presenter pointed out, there's lots of social engineering, lots of reconnaissance that you have to do, things that don't necessarily require physical access, and those are all very important parts in your hacking kill chain, as I would call it. And yep, to me now, this is what as any educated person that knows what a hacker is, Mr. Robot is clearly the most realistic here. So, yep, this is, going back to a book that was released back in 2017 called PCB RE Tools and Techniques. Highly recommend this book. And it goes into detail of how to actually reverse layers of circuit boards, because there's multi-layer circuit boards. As a matter of fact, I worked on boards, even in my previous internships, that are as much as 40 layers, which is kind of cool. And now that with a lot of the imaging technologies like X-ray, CAT scans that are available for failure analysis, you can very in-depth go through each layer without even destructively going through all those layers as well, which is kind of cool. And so yeah, as I mentioned earlier, we're mostly focused on levels 0 through 2 here in this talk, because I think that explains kind of most of our skill levels here in terms of hardware. Yeah, level 3 maybe, but level 4 to 5 is where you start to see actual corporations or nation-state level attackers having those kinds of equipment. But that's quickly starting to change now that, yeah, there's more equipment that's being proliferated. Yep, so, yep, oh wow, just mentioned that's completely. Yes, so most hackers rely on documented vulnerabilities, as we all know, CVEs and such. And many of these IoT devices, as I found out in previous experience, run firmware that's derivative of firmware that's 2 to 5 years old in some cases. And it's not uncommon for designers like myself to use the same operating system or firmware that comes with a dev board and not really do anything much with it. And so sometimes, I don't know, as an oversight, we don't even change the admin password on it. And we don't really patch it, and that's what we just send out into as a product. And so, and once again, it's very easy to find these development boards. Once you find a system on a chip or whatever microcontroller they're using, you can usually find the dev board for that part or very close to it. And there's a ton of documentation on that, like very rich resources from all your parts vendors as in the form of data sheets or applications guides. All those exist. And as most of us know, yeah, many IoT devices don't even receive consistent over-the-air updates over time. So going back to that point that not only is the firmware maybe even 2 to 5 years old and is a derivative of it, but they're not even updating that over time. And these days, it's very rare for a non-state sponsored black hat hacker to find a 0-day in most of these devices. I mean, it happens, but it's still pretty rare. And once there is a documented 0-day in something, and knowing that a lot of these things don't get patched over time, some of these things are end of life, then you pretty much have free reign over someone's network once you access one of these devices. Going back to this point. And so, devices that are available to anyone here. There's the Chip Whisperer, which is a really cool side channel analysis tool, which you can use to do clock and power glitching. So that is that on a microcontroller or a system on a chip that uses an external clock or a power source, you can actually kind of just throw in a couple probes or wires onto that clock, tap in, and then you can make it skip instructions or like actually glitch. So if you glitch the clock like quickly, so if you double the clock speed that it's going at, you can skip over instructions and maybe do something interesting. And this is from this company here. And they also now have a few new products that go with into Ethernet and other PHY interfaces now, which is kind of cool. And all those devices vary from like price range of like $100 to $2,000. So pretty easy for someone to pick up if you're really dedicated to it. And then one of my favorite tools is the HackRF, which pretty much covers any wireless IoT device you would ever want to hack, because most of the work you'll ever do is between 1 megahertz to 6 gigahertz and 20 megasamples per second, which is like around 20 megahertz of bandwidth, basically, is equivalent to like a Wi-Fi channel. And so you can pretty much do almost, yeah, it's just basically like a workhorse if you're planning on doing any RF protocol analysis or hacking. Pretty nice. And then another thing, just to mention it for the sake of mentioning, is the JTagulator. So as I mentioned, lots of vendors they just don't they just always leave the silkscreen labels on. And if you see something that says JTag, if you're lucky, it's probably just the same pinout of any dev tool that they've used, which is, you can look those up, very standard pinout. But if they went to the effort of obfuscating it, which is still not security, you can use this thing to unscramble those pins in a smart way. Oh, whoops. Yeah, so other inexpensive tools. So as I'll mention, like with pricing, the BusPyre and GrayFed are two very nice tools now that exist that you can do pretty much also anything with. And then there's also even this logic analyzer if you want to detect stuff passively. That's like only $20 from SparkFun. And using SIGROC, which is a open source tool for actual logic analysis, is very nice as well. And so there. And yep, if you get into any hardware hacking, I highly recommend this iron, just the FX 888D, because you can, it has removable tips, and they're $7 to $10 each if you get the genuine ones. If not, you could probably get, I think, even on Amazon, a whole bundle of like non-genuine tips for about that price. But the point is that if you want, because the vast majority of IoT devices or consumer products are surface mount tech and surface mount devices, that's kind of where that comes in handy, because your old Radio Shack iron that comes with a fixed tip or one that you get from Harbor Freight definitely will not work. It'll definitely mess up and burn the board or take some pads off traces and stuff. Yep, so some very prominent examples of hardware hacking. So almost every year since 2017, right? If anyone can correct me on that, there's been the voting machine hacking village. And there they've pretty much been able to access all those via hardware access. And I mean, some of them, as some of you may have read in the news, they have USB ports out in the open or other kinds of common interfaces. I actually own one of the ones that I actually voted on for the past 3 years. It was like a Diebold voting machine, and I was so glad this year that they replaced it, because I was like, oh, I don't want to vote on a voting machine that I own and have taken apart. It's very sad. It's very depressing, as some of you may know, in our current political landscape. So yeah, this is one of my favorite attacks. Just like this casino had a internet-connected fish tank monitor, so it's just like a simple temperature sensor, humidity sensor, and the hackers were able to actually do some recon, and they found that, oh, there's this temperature sensor on their network. I wonder what creds it uses, and I think it turned out to be that they were the default ones. And so from there, they were able to pivot through the network and pwn the casino. And so, yeah, and then, yeah, going on to now, obfuscation is not security. The most common method in almost every hardware device I've taken apart is, you'll see like epoxy over debug ports. I mean, come on. Like, there's what you just Google, like, oh, how do I take off epoxy? Like, just go to the hardware store and then get a couple of chemicals to take it off. Scratching off parts, part numbers off of ICs, very common. I mean, yeah, if your Google skills aren't that great, then okay, you might be out of luck. But once you know that through using a multimeter, if you know where the ground pins are, the voltage pins are, it's pretty easy to figure out what part it is. Also based on like where it is in the circuit. Like, okay, if it's in the digital section, okay, it's there. What other parts is in there? Then you can kind of just go back and reverse engineer that, and then eventually figure out what part they use. And I still find it rare that a lot of these companies go to an effort to actually make their own dedicated ASIC, because I mean a lot of these companies are just there to buy 10,000 of whatever part off of DigiKey or Arrow and then be done with it. And yeah, as I mentioned, a good multimeter goes a long way. So yeah, in my experience, the Harbor Freight meters don't work that well. I don't even think like the lowest end model comes with a good continuity function. And in my experience, one is blown up in my hand when measuring AC voltage, so not a good idea. I recommend Fluke for sure, or pretty much anything above $50 will do will not only be good for your hardware reverse engineering work, but will be one of the best electrician's tools you can use in your house as well. And even supposedly NDA'd parts have their data sheets leaked onto the web. And so where this is prevalent is you see a lot in China on like social media sites like Baidu or even like in Russia. It's really funny to see like just websites with like a .cn or .ru ending and just finding like, oh, they have this data sheet there. How'd they get that? I mean, I'm not gonna ask questions, I'm just gonna download it. Maybe get a virus in the process, but yeah. That's why we do this in a virtual machine, right? Yeah, that's right. Okay. So as a designer, one of the easy ways to make it harder for adversaries to attack hardware is by using more complicated packages, so like BGA packages, which are bulk grid arrays. So like these are actually like soldered spheres that are in a grid under a chip, as I'll show here later, maybe there. Yeah, so this picture shows it. And there, if you route everything internally through a board, that almost will thwart almost any effort that a low-level hacker will face, because they have to destructively sand off layer by layer board or whatever method that they use to find all the traces. And then if it's an expensive device, it's not going to be worth it at that point. So like once again, this is just basically just a obfuscation method that's kind of built into how you design a board. But once again, it's not the answer, but it helps. So if you do this along with removing any through-hole headers for access, just kind of going with surface mount test points, and that's how you program your boards, is like with like a pogo pin jig and stuff. At least that'll throw a lot of adversaries, because I know a lot of people aren't good at surface mount soldering, so that'll help. And then yeah, removing silk screen labels helps a lot. Removing part markings helps. But once again, none of these even together are the solution for building a secure product by any means. And so Yeah, and then this technology exists. I actually don't even know how much it is now, but actually putting devices inside a PCB. So as I mentioned, I worked on boards of up to 40 layers, and when you're spending that kind of money, you can afford to put even embed components inside a board, which is kind of cool. So it's very expensive, as I mentioned, but it's a way of thwarting most of your lower level adversaries, unless, of course, you have a lump sum of like $8,000, take it to a local university, or if you want, maybe even fly. I've seen someone actually talk about this. Go to an airport, buy a flight ticket, right, and get TSA to X-ray for you. Maybe ask them nicely, hey, can I take a picture? Yeah. So, and of course, if you're very serious, so I think as far as the consumer space goes, well, like a lot of the vendors for modems and such, they do utilize some anti-tamper measures in like their modems and stuff in networking hardware. But even in most consumer hardware, it's very rare to find that. I mean, you might find these in point of sale systems where if you open it up, then it just erases whatever memory is on it. But yeah, this technology exists. It's existed for years. There's even embedded resistor fuses where if you put a multimeter in the wrong place, it'll just burn up the resistor like it's like a fuse. Because if it's like a 1.8 volt circuit or something, and because a lot of how these continuity tests on multimeters work, like a lot of multimeters will put out either like 4 or 5 volts on there, 3.3 maybe even. So if they're exceeding anything digital there that are like 1.8 or lower kind of voltage, and if you put these kind of protective devices around a part, then those kind of act as anti-tamper fuses in a way. In a way, yeah. And so, as I mentioned earlier, there are so many systems on a chip that you find nowadays. So I think this one, if I recall, was I think in an IoT device I later took apart. And like, look at this. Like, I mean, not only do you have ARM trust zone, which a lot of these come with now, but there's secure JTAG, secure fuses, secure memory, secure real-time clock. I don't know, and then actual tamper detection features. So like, you can actually put all these previously mentioned systems or parts in there in your circuit or in your board, and then utilize those as kind of like a full security solution for your product. But do vendors actually implement this? No. Why? Because it's expensive. Until they get breached, and then they'll start doing it. And yeah, once again, there's lots of crypto out there that exists. The common excuse, and sometimes valid, is that it does use up valuable processing power if your thing is running in real time. But you're starting to see, even with these kinds of chips, dedicated crypto hardware or engines to accelerate that process. And there are parts that you can get for under $1 now, hopefully even less now, where you could just buy like a little chip that does that for you out of the box or out of the system. And so, yeah, as I mentioned, these exist. And so, like, I guess this one is, yeah, so this one is the deep cover series for Maximum Integrated, and this one actually implements even silicon anti-tamper measures. So if you try to tear the chip apart and decapsulate it, so that's with like using acid or sanding, then it'll actually just destroy the contents of the chip at that point. It just renders the key useless. And then so, yeah, this is the features that are in that chip as an example. So I don't know if it's written in here, but yeah, as you can see, there's like numerous symmetric, asymmetric keys that you can create with that, as well as I think even like a true random number generator implemented, or true random number generator. And then as many of you might have in your computers, there's the trusted platform module, but as we found out recently, there's some interesting attacks on with clocking or clock glitching that they're kind of that might be susceptible to actually now. And so yeah, here's an example of a board that a couple of my friends and I actually took apart too. It's called the Wink Hub, and I think this was specifically the first generation of this device. And as you can see, this pretty much has everything like written all over the board. Like, it's kind of like a hacker's like just buffet of like things to hack at this point. So, and the nice thing is that I still haven't done this, but if if you're able to pwn this, then you can also use it as kind of like a test bed for like your hack RF or software-defined radio to play around radio protocols, because it does have everything that a lot of IoT devices use. And so here I found like, oh, there's the JTAG for this Electron wireless interface. There's this JTAG for the sock that's on here. And then the UART for it, as well as for Zigbee, the KID, which they do carbon monoxide and fire alarm or smoke detection kind of stuff. And then there's Z-Wave, and then there's just a whole micro USB port on the board there that they never bothered to. So this is the kind of thing where it's like, this was their prototype design, and they just said, oh, ship it. Just because it's just cheaper sometimes to do that, but at the same time, you risk a lot of security. And I think here there was an Ethernet port there at one point too. So, and as a few of us found out, there was a documented attack where if you just short the address 0 of this NAND flash, you can get this to just go back into a fallback state of into U-boot, and then you pretty much just have free reign over the system that way. But mind you, that's a physical attack. So as far as remote attacks, I'm not aware of how you can remotely attack this system. And yep, here I mentioned this book. This book is awesome. And it really goes into kind of like the perspective from a designer as well. Like I forgot what chapter it is, but it's like chapter 2 or 3, where it puts you in the kind of like the shoes of a designer and like how they design a board and stuff. And it gives you a very interesting perspective from as a design engineer. And so, yep. And then there's cool semiconductor reverse engineering attacks, and then I also just linked in exploiters because they always work on the cool IoT device hacking. And then, then we're going to move on to, so in here I mentioned that there's an attack called thermal laser stimulation, which sounds like it's kind of like science fiction, but it's not. Okay. I don't know if this will work or not. So this let's put it this way. So this is a tool that is used for failure analysis. And a lot of universities actually have this, where you can actually send them a chip, or they'll look at a chip for you at the low cost of $8,000 per day. I mean, billing hours, right? And then they'll image a chip. And so how this technology works, which is interesting, is because so there's also something called Electro-Optical Attacks. So that exploits the property of semiconductors, where if a transistor switches, it emits a photon. And so that's how you can look them up online somewhere, but you can actually see cryptographic algorithms running in basically just with like a picture like this or a video, and you can see all the bits firing, or all the transistors firing and emitting their photons. And here, instead of using photon emission, it uses thermal emission, IR, infrared emission, at the microscopic level here, or the nanometer level. And I've even heard that there's even tech now that you can image all the way down to like 5 nanometers of like an entire chip. And so I don't think I've linked it here, but they were able to, they've actually been able to image a whole like Intel i7 or whatever of the 14 nanometer node. I don't know if they're going to do a 7 nanometer yet, but once again, the technology exists. It's very interesting to see that the proliferation and development of all this failure analysis tools and all this used for hacking and other things is starting to get only cheaper and also more available. So yeah, and here it's kind of cool because they were able to extract a battery-backed RAM key from this FPGA. And what they're showing here is that they're able to actually kind of like toggle some of these registers and transistors in there. And yeah, difficulty moderate to hard. It's really about money at that point. So it's just a fun attack. And let's go back. Yep. Oh, whoops. Going back. Yeah, so conclusion here. Overall, IoT devices, even in 2019 now, still have a long way to go in terms of security. they need to be implementing all these features that are included with their microcontroller or microprocessor that they chose. I go to a lot of events from actual like vendors, and it's always a little bit nice to see the fact that they're actually now producing microcontrollers that do have further security measures. I don't know if I don't know if any vendors have started using them yet, but once again, they're starting to exist more and more, and hopefully getting cheaper so that all of our personal information is protected, right? I mean, I want to buy some of these devices, but yeah, it's kind of a scary world right now. And so there are many effective, low-cost, and even free PCB RE countermeasures that I mentioned. And once again, this was a presentation that I gave to basically a lot of vendors at the time, and that it's this is to reduce monetary loss, your IP, and all that. Like, as a designer, that's what you want to do. You don't want a huge breach to happen, and then your entire reputation is just tarnished. So, and yeah, verify hardware security using the tools mentioned in this presentation. So, any questions before I?
So for the hardware security for like PCBs and things like that,
Yeah.
are you mostly worried about, say, IP, or are they
Yes.
worried, or what kinds of attacks are people worried about? Are they worried about there's hardware in transit and someone's going to mess with it, or what?
The answer is yes to all of those. Actually, yeah. Restate the problem. Yeah. So he asked if what was it? Actually, if
Oh, sorry.
Yeah.
So it's like, what are people trying to protect?
Okay, so what are people trying to protect? Are they trying to protect the actual design or intellectual property, right?
Yeah.
Or the data in transit on the board? And the answer is yes to both of those, actually. Yeah, because I mean, at least from where I work in the defense side, you want to protect everything there, because you don't want an adversary to know at the nation state level how the board's working. But at the same time, I feel like even like a lot of these commercial vendors have to accept this idea that, I mean, it's pretty much well known that your board's pretty much compromised when they have physical access. So you have to design knowing that. So that's why you have to start encrypting all those data communication channels, as well as the actual like operations on chips. So that's why you utilize things like ARM Trust Zone. You use Secure Boot. You make sure to use whatever cryptographic accelerators they have to protect any contents in RAM also. And also any other kinds of like privileged data over any of like the standard protocols like I2C or SPI. They all now support some form of encryption to an extent. So if you're running sensitive data over those kinds of things, then please use encryption. Yeah. Yeah.
Also comes down to what the device does. He was playing around. He got a garage door.
Oh yeah.
Toyed around with on his phone, and he was able to find the identifier for his garage door. So if you can go in and exploit the communications from intercept that traffic and manipulate it, you could open somebody else's garage door, which would give you physical access to
Okay.
So depending on the device, you've got to put a threat actor and then design a scenario on it. Say, well, could they do it?
Yeah. And that's another thing. So as I'll mention in the audio, so Jared, our previous presenter, mentioned that with garage door openers, or like a friend of his that was working on garage door openers, was able to find the ID of it. Yeah, the ID for his door. Okay. Oh wait, is that Sammy Camcar? It was that Sammy Camcar? Oh, okay, because I know that he worked on something like that. So okay, yeah. So and then the other part of the story is that he worked with his friend of his worked on with another friend on the West Coast to try to see if they could open a garage door based on whatever security was implemented there, and fortunately it didn't work, right? As you said.
Yeah, it was. We were exposing some information, but they had intended checks to make sure that if that became exposed, that they could shut down the actual attack.
Yeah. Okay.
And I think to take it serious, so you start thinking about medical IoT devices.
Yes.
Think of all the healthcare information that you could glean off of somebody, or if that could be manipulated, actually kill somebody.
Yeah. Yep. I mean, we've seen ransomware take over hospitals, right? And I mean, what's stopping that from pivoting or jumping over to all those devices that are, keeping someone alive, right? And the interesting fact that I learned recently is that apparently a lot of medical devices also run off of CAN bus, which is really weird to think. Like, that's actually one of the protocols, which is the same protocol in cars. And if a lot of you people know, have been reading news articles and such in the last 5 years, I mean, the state of car security is pretty bad as well. The CAN bus was a protocol that was developed in the late 80s and early 90s and doesn't support any form of data authentication or anything. So you could pretty much just do a man-in-the-middle attack there and spoof packets. And then, for example, in a car, press the brakes or press the accelerator or just kill the engine while someone's driving on the highway, as a few YouTube videos have shown. Yep, so I don't know if there are any questions, but yes.
You mentioned if you have like part numbers scratched off of an IC, you can use the package and knowledge of here's a ground pin, here's a supply rail to reverse engineer what that chip is. What's your process for that? Because
Okay.
I don't think there's a search engine, although I want to
That's true. Yeah. So as okay, the question is, so in going back to the slide, actually, that's probably the best idea. So how do you figure out the pinout and then also then the actual chip of a chip that has the part number erased or scraped out? Actually, did I actually have a slide on that? I don't know. Because I think it was just the obfuscation one. Yeah. So the question is, like, how do you determine, based off the scenario where the part number is scratched off an IC, there's other things that are obscuring the part number. So CME Camcard did a very good talk at Hackaday Super Conference back in 2016, of course, where once you figure out the package, what kind of it is, so all that's publicly available because a lot of silicon manufacturers as well as parts manufacturers, they stick to very specific packages. And so you can use, once again, the power of Google to figure out, okay, this could be like a TQFP, so like a thin quad flat pack or whatever. And then from there, you can determine like, okay, so it's this dimension. So, and using tools like, for example, there's now, I don't know if anyone knows, but there's circuit board rulers or the references where they have all these parts or like the actual like footprints for them, and you can compare those, and then from there you can kind of assume or derive that, oh, okay, it's probably this part package. And once again, it's an iterative search process where you're just kind of constantly checking like, okay, it's probably this package. Based on where it is in the circuit, I probably know what the function is. And so when you look at it as like where is it, like on a lot of the parts vendors' websites or distributors, they organize all the parts by function and application. So based on that, like you figure out eventually like, oh, it's this application, it's in this package. And so now you might have a list of 1,000 parts at that point. And then based off of that, once you do with a multimeter kind of check where the voltage pins are, as well as the ground pins, and maybe if you're lucky, a few data pins, you can, through some clever searching, as Sammy Camcar points out, you can, if you do it good enough, you could probably match all the pinouts that are mentioned in a PDF of the data sheet. And then if you're that lucky, then you have the part, then you just get the part, of course. But once again, this is almost like that's never guaranteed for sure. Like that, like because what was it? I mean scratching, yes, but because once again, it's a very good method of obfuscation, but that's not what you should have as, that's not a security method at all by any means. So going back. So once again, going back to once you start probing it, and then, for example, using like the logic analyzer I pointed out, like the $20 logic analyzer, if you know that, okay, it looks kind of like SPI or I2C, and then from there you can kind of determine where the data pins are, what configuration they are in, and you can decode the data, then you might be able to figure out functionality even further. And so, once again, there's no direct solution to what that part is, but it's a combination of like, oh, it's this package. I know where it is in the circuit. I kind of can infer the application of it, as well as based on the pinout that it's, okay, it's probably running like 5 volts, 3.3 volts. And then remember on DigiKey, you can even search by what voltage they're at, which is kind of nice.
So you're largely going, I know it's this package,
Yeah.
I think it serves this purpose,
Purpose.
I know it's this pin pitch, and you're just filtering on DigiKey.
Yeah,
It supports these interfaces.
Yeah, correct.
You filter down and then you start looking
Yeah.
at data sheets.
It's a highly iterative process of using all the filters on DigiKey or any other parts distributor's website, where it's like once you know all the parameters, like all like the specifications of the part, because you can reverse engineer those from like a multimeter or whatever, then oh, we got it. Yeah. So sometimes it's that simple. Maybe you might get the list down to 100. Then you just start opening data sheets and then comparing the pinouts one-on-one. Because sometimes you don't know for sure the data pins are data pins, but you know for sure that I know where the voltage pins are and the ground pins, because those are always the first ones that you find are the easiest. Like ground is especially easier. And the nice thing is that as a designer, the reason why you want many ground pins is for signal integrity and other like non-ideal properties of circuits, which is another rabbit hole that I won't go into. But the purposes of having a lot of ground pins on a part is so that the signal has a nice return path so that it doesn't mess up anything else in the circuit because of weird electromagnetic effects. And that's how far I can at least explain that simply in simple terms. So yeah, it's a very complicated process to design. But the cool thing is that, you know, of course, if they mess up that implementation, you can use kind of like these cool electromagnetic side channels to sniff out data and other things. Because, you know, if they've effectively created a radio transmitter, it's only a matter of time before someone figures that out. So, but yeah, once again, restating that point, to find a part that the package is obfuscated, you have to be very clever in using the search features on DigiKey, determining like, oh, it's this package, this is the voltage. All those parameters have to be iteratively figured out in order to find kind of like a narrow list of like 150 parts or so. So, yes, thanks.
Thoughts on your inexpensive tools list? What are your thoughts on the secret?
Oh yeah. Actually, that's a good point that you pointed out, because I remember attending that event locally that mentioned that. So the Shikra, which is FT232, what was it? 2322H, I think is what the FTDI part is. So that's a very nice board that uses that chip. I forgot what other parts use it. I think, going back to my tools list. So the reason why that's a very good tool is because, as I pointed out, there's the Bus Pirate. Now, the Bus Pirate, it's capable of JTAG and other interfaces, but it's very slow at it because the FTDI chip that they use on there, which is I think it's just the normal FT 232H, is just like basically just like a serial kind of decoder with a few I/O pins, and that's definitely not like actually designed to do JTAG well at all. And so the reason why, yeah, like a tool like the Shikra exists is because if you want to do something a little bit more efficient and cleanly, it also has more actual like a dedicated interface for JTAG. That's what you use. And I think, for example, with like the Great Vet, this is another new tool that came out this year, finally, that actually has, I think, even faster interfaces than the Shikra possibly for accessing JTAG and other protocols. So, yeah, and well, I think the Shikra is only like $20 or something also. Yeah, 45, yeah. I know that you can also get that specific part number, the FT2322H, off of DigiKey or Aero, like the actual dev board with all the pins broken out for like around $20 or so. So that exists. Yep. So yep, good point. Good point. Yeah, good call out. Yep. So going back to the end of this. So once again, I mentioned that if you want to look at more interesting state level attacks versus other attacks in general, there's a lot of links here. Yeah. Once again, so the most exciting attacks now are these, because those used to be exclusively reserved for nation state level attackers, because these are all failure analysis tools that are now being used to now attack semiconductors and other types of hardware. So once again, so for example, going back to that one slide I showed you where you're looking at a battery-backed RAM from a thermal laser stimulation process. So the reason why that tool exists is because a lot of semiconductor companies they want to figure out why their part failed in field or wherever under certain conditions. And so how they can figure that out is that they can look at the individual transistors at that resolution and figure out, okay, if I'm operating at this temperature or these other parameters, then the transistor will exhibit these properties. And that's there for recreating failure scenarios and such. And the cool side effect of that, and also the scary side effect, is that those can be used to attack and observe. So I think the one hardware hacker and author, Bunny Huang, says it best that you can't obscure atoms and electrons at this point, because we've really gotten down to that level now, where everything kind of needs to be implemented in software, sort of, when you're dealing with all these nation-state level attackers. So like everything on that level, if you're putting anything sensitive on a chip, it has to be at least encrypted or whatever to whatever key and such. And because if it's in plain text, then they can just read it right off, and that's kind of the scary part. So, yep. Hopefully, any more questions?
So for some of these like laser things, or they're scanning with light.
Yeah.
Like I can't imagine like someone using that on like a Core i9 or something.
Yeah. Yeah.
The features are so tiny, right? Like you'd be shining ultraviolet or like X-rays on it or something. So,
Yeah.
But is it for more like other pieces on the board or something like that?
So once again, going back. Yes, going back. So once again, a lot of these tools to begin with were failure analysis tools. They weren't designed to be like, so in order for you to use them to be attack tools, you actually have to modify them further. So nothing out of the box works as an attack tool. Like, so okay, restating the question again. So he was asking that, I mean, how do you use all these systems or these newer techniques to, like, for example, not fall injection attacks, but the newer imaging attacks like electro-optical and thermal laser stimulation for attacking devices. That's right?
Yeah.
Because on such small feature sizes, like on the newer 14 nanometer and 7 nanometer processes. So as I mentioned, a lot of those technologies now are getting down to like the 5 nanometer level. They've actually now have even gone beyond the current production process nodes. So that's something that keeps me up at night, actually, thinking about that, because when you're designing an ASIC now, I mean, you pretty much have to you have to think a little bit more than just like let's build an ASIC. Now you have to worry about, okay, we know that they can image this and pretty much reverse engineer the entire circuit. So how do we protect or obfuscate it further in a destructive way? So a lot of technologies that are in the pipeline are like actually adding devices to the back of a part. So if you try to remove it, it'll just crack the IC and then render it completely useless. So another cool technique is, so for example, like on an Intel processor, I mean, you could put a detection device on the heatsink, and then if someone tries to take off that heatsink, it'll just zeroize whatever is on the part or whatever is on the system. So there's a lot of clever tricks that still have yet to be developed that you could probably implement now. But that's definitely one of the things that keeps me up at night, for sure, are these attacks. Electro-optical probing and thermal laser stimulation.
Is that trick with the heatsink being done? Because you should suggest that. I
would like to think it is, because it's a fairly simple one. Yeah. I don't think there's like anyone stopping from anyone from implementing that. So
you're not going to generally see a photon get through.
yeah, exactly. So whoops, if I can go back. Oh my gosh. Yeah. So, actually, another mention is that, as it turns out, so a lot of supply chain attacks. So that is that putting a Trojan, like an actual like extra circuit inside a chip, might be a lot harder to do than what a lot of people think. That's what a lot of people focus on. But what a lot of people don't realize is that there's a lot of other things that are easier to exploit or hack into along that entire supply chain rather than during production, but with vendor tools. So if you can compromise the vendor tools, so like that's like the programming software and such.
So the thing that's generating
Yeah,
design and
exactly. Yeah, exactly. And there was a DEF CON talk, either it was 2 years ago or so, where I think it was Somerset Security from California was able to compromise one of the JTAG tools and insert malicious code, and then that could insert like a hardware Trojan or such into a system. And so that by far is easier than actually like trying to infiltrate, for example, like TSMC in Taiwan, the world's biggest foundry, and then trying to try to hack in their systems, or at least do a physical attack there and insert a malicious circuit. Like that's a lot harder to do because I mean, not only guns, gates, and guards, but they also have other measures for detecting any additional circuitry that's added and stuff. And I think there's at least like, once again, it's like a whole team of people that have to verify and implement those kinds of things. So if it happens, then at least one other person will know about it, because there's a lot of that, at least like a two-person or two-man integrity kind of going on when they are creating those kinds of parts. So yeah, just thought it was worth a mention, because a lot of talk nowadays is like, oh, how does an attacker get into the supply chain? And yeah. So any more questions? Yes.
Sometimes you may be reverse engineering a PCB and you'll actually find the JTAG error.
Yes.
The various debug lines. But then let's say you run something flash, and then you've got a lockpick in your mode.
Yeah.
Do you know of any way of getting around that without having to actually restart?
So that's funny that you mentioned that specifically, because the person in the back mentioned that once you find JTAG or any other port that's used to program the part, how do you extract the contents of whatever like EEPROM or other storage medium that whatever of interest that you have, and there's a lock bit, there's like one little simple security feature or obfuscation feature that prevents you from just attacking the device. So let's see, at least for us on a hobbyist level and such, there's nothing we can really do about it unless you start accessing actual like chip level tools. But I will mention that I think it was Bunny Huang, the hardware hacker himself, did an attack on on a chip where he was able to reset it by, once again, scraping off the chip, kind of putting some tape around areas he didn't want to hit with light, and then he was able to reset the fuses that set that lock bit. And once again, that took a lot of time and effort to do. You can't just do that out of the box, of course. So he did some interesting stuff where he used just kind of like a mirror to aim and focus the light onto one spot of the chip, and he was able to successfully actually reset the fuses that set that security bit, and then just dump the ROM on it. So once again, it's possible, but it's about how much time do you have, and then and it gets so much easier once you actually have access to the imaging processes that I told you about now. Yeah, because once again, these attacks are I mean, I always heard about these as failure analysis tools. I did not realize that they were getting only cheaper, and that universities started getting them and actually developing some of the tech. So and once again, you can ask them and they'll do it for you for whatever a labor cost it is at the time. So any further questions on hardware security? Anything? Yeah. Okay. No problem. Yeah.